Welcome to Zoominario. Today, we're very excited to have Tanya Garcia. Tanya is an Associate Professor of Biostatistics, Provost Distinguished Faculty Leader, and a Tyson Academic Leader at the University of North Carolina at Chapel Hill. She earned her PhD in statistics from Texas A&M University and has led a transdisciplinary research team focused on designing robust statistical methods for neurodegenerative diseases. Dr. Garcia has received continuous funding as Principal Investigator, including an R01 from the National Institute of Neurological Disorders and Stroke, and is committed to mentoring the next generation of statisticians through grantsmanship and leadership training. Thank you so much, Tanya, for accepting the invitation.
Yes, no, thank you so much, Claudia, for that kind introduction. So today I'm going to talk about unlocking hidden clues, differentiating censored and missing data to decode Huntington disease progression. So this is a project that I worked on jointly with my wonderful team, my current PhD student, Jesus Vasquez, my former PhD student, Marissa Ashner, she's now faculty at Duke, my collaborator, Yan Ma at Penn State, and my other collaborator, Karen Marder at Columbia University. This project was funded by the National Institutes of Health and the National Science Foundation. So I have built my entire career as a biostatistician, and it might surprise you to learn that I actually knew nothing about biostatistics until my very last year as a PhD student. Up until that point, I was playing with lots of theorems and proofs and working with what felt like the entire Greek alphabet. But all of that changed in my very last year as a PhD student when I was introduced to this rare neurodegenerative disease called Huntington disease. Now, for those of you not familiar with this disease, you can think of it as this cruel combination of Alzheimer's, Parkinson's, and ALS all wrapped into one. In short, it's a truly devastating disease. But there is hope because out of all the neurodegenerative diseases, we know its exact cause. So back in 1993, scientists discovered that Huntington disease is caused by mutation in the Huntington gene. That mutation is a triplet repeat expansion of cytosine adenine guanine, or CAG for short. So basically, if you have more than 40 CAG repeats in your Huntington gene, you are said to have this gene mutation. And what that means is that with a very simple blood test, anyone can learn if they have this gene mutation. If you have it, that means you will develop Huntington disease. And if you don't have that gene mutation, you won't. Now, certainly, the results of that genetic testing can be truly heart-wrenching. But from a scientific perspective, being able to identify with 100% certainty who will and will not develop this disease gives us hope. That hope is in the ability to study individuals with this gene mutation years before symptoms even show up. By studying these individuals, we can learn how Huntington disease progresses over time so we can identify when and how to best intervene. So there's been many different studies on individuals with this gene mutation. And one of them was this observational study of about 1,300 individuals with this gene mutation. They were followed for about 10 years, and different data was collected on them, one of them being this measure of symptom severity. So on the y-axis is the symptom severity score, where higher numbers mean worse severity, and the x-axis is the number of years in study. Each of these gray spaghetti lines represents the symptom severity measured over time, and the dark solid line right here, that's the symptom severity averaged across all individuals. And we call this line the average symptom trajectory. So looking at this plot, it looks like this symptom trajectory appears to increase and then decrease. suggesting that symptom severity initially worsens, but then gets better. And that result really goes against what we know about Huntington disease, because many scientists have shown that Huntington disease is progressive, meaning it's supposed to get worse over time. And the reason we're seeing this result is because of how I plotted the data. So individuals who enter this study enter at different disease stages. Some are more advanced and some are less advanced. And so by me plotting the data in terms of years in study, I'm completely ignoring that fact about differences in disease staging. So there's been many ways to try to address this issue. And one of the more popular ways is, instead of using years in study, it's to use the time axis years to diagnosis, which is what I've done in this plot. So in this plot, 0 represents when an individual is diagnosed. -6 is 6 years before a diagnosis, and +4 is 4 years after a diagnosis. So by doing this time shift and shifting the data, we now get a more realistic conclusion in that far away from a diagnosis, the symptom severity is low or minimal. It gradually starts to worsen and then continues to worsen after a diagnosis. So this picture here, it's much more representative of what we know about this disease. But if you compare this plot with the previous one, you'll see that there's a lot fewer gray spaghetti lines. And the reason for that is because I deleted data. And the reason I deleted data is because to make this new plot, I have to know when an individual is diagnosed. Because if I don't know that information, I don't know where to put their gray spaghetti line. I don't know if to put their symptom trajectory here or over here or over here. And so this is one of the big challenges with Huntington disease, in that we don't always know when an individual is diagnosed. And the reason for that is because this disease progresses very slowly over decades. So sometimes in these studies, the study will end here and an individual will reach the criteria of diagnosis so that they will be diagnosed before the study ends. In that case, we would say that their time to diagnosis is known. But because this disease progresses very slowly and not all the studies last for a very long time, it's often the case that the study will end here, but the individual is not diagnosed before the study ends. Now, because these individuals have that gene mutation that will lead to this disease developing, we know that this individual will be diagnosed sometime after the study ends. We just don't know when. So in that case, their time to diagnosis is not known. Now, even though we don't know when exactly this individual will be diagnosed, we do know that will happen sometime after the study ends or to the right of the study ending. And so for that reason, we say that their time to diagnosis is right-censored. And so this is the problem that motivated our statistical problem. We wanted to find a way to model these symptom severity scores as a function of time to diagnosis, where that time is not known, it's right-censored. And so this is the problem known as a right-censored covariate problem, because it's this variable, this covariate X, that is right-censored. So to start tackling this problem, we started with just a very basic regression model, and that we're trying to relate an outcome Y to covariates X and Z. And so in our problem here, when the individual is diagnosed before the study ends, their time to diagnosis X is known. And otherwise, if the individual is not diagnosed before the study ends, their time to diagnosis X is not known. It's right-censored. So our goal in this problem is we want to find a way to estimate these unknown parameters, beta and sigma squared. basically, can we find a way to estimate theta when we don't always know X? So that problem of not always knowing X may make you think of another type of problem known as missing data. Because with missing data, we also don't always get to know or observe the data. So this idea of X being right-censored is very analogous to X being missing, because in both cases, sometimes we know X and sometimes we don't. So that similarity led my team and I to dig deep into the missing data literature. We thought that perhaps we could take a method for the case where X is missing and apply that to the problem where X is right-censored. And because they're so similar, we could get some great results with that approach. But when we did that, we got some unexpected results. When we took methods designed for the case where X is missing, the methods worked beautifully. It gave us the results that we were absolutely expecting. But when we took those same methods and applied it to the case where X is right-censored, the methods did not perform well at all. So that conundrum led me and my team to go back to the drawing board. We reread all those papers, we double-checked all of our code, but after months and months of trying that, there was really no progress whatsoever. And so finally we got to a standstill and we didn't know what to do. So I finally asked my team to basically adopt a concept known as beginner's mindset, where the idea here is that let's put aside everything we think we know about missiness and right censoring and just approach this problem as if we were a beginner. Let's try to ask all these basic questions to really try to understand this problem. And it's when we did that, that's when we started to make discoveries. So we dug deep into these methods with that beginner's mind, and we identified 5 different methods from the missing data literature and saw how they differ when the problem is right-censored. So we looked at these methods in many different aspects, and two of those aspects were something called robustness and statistical efficiency. So by robustness, I mean that these methods rely on certain key aspects we call distributions. And the idea with robustness is that can we misspecify those distributions, so assume wrong distributions, and still get the right result, still get the correct estimator that we're interested in. So this is the robustness. The ideal situation is that we can be very wrong about these distributions and still get the right result. Statistical efficiency is about variability. We want a method that gives us an estimator with very low variance, or which is the same as saying high efficiency. So we had found these 5 different methods. We identified their properties, and we showed that yes, these methods can apply to both X being missing and X being right-censored, but the methods need to change in order to work properly for the right-censoring case. By digging deep into these methods, we also saw that their properties change depending on whether you have a missing data problem or a right-censored problem. After having identified those methods, we applied those methods to this large ongoing observational study of Huntington disease called Enroll-HD. So I started this talk by saying that one of the interests in the field is modeling how these symptoms change over time, this symptom trajectory. And one of the symptoms of key interest for patients is cognitive impairment. Because with cognitive impairment, that can really affect an individual's quality of life. So Enroll-HD collected data on cognitive impairment, and one of those measures is something called the Symbol Digit Modalities Test, or SDMT. This is a cognitive test that measures the coordination of visual scanning, working memory, fine motor speed, and concentration. So what we did is we modeled this SDMT score as a function of time to diagnosis while accounting for something called the CAGH product score, which is basically a measure of disease burden. This idea is it accounts for the genetic mutation and how old the patient is. We applied this model to the following individuals. These were individuals who were genetically confirmed to have the gene mutation, so they will eventually develop Huntington disease. They were not diagnosed with Huntington disease at baseline because we were interested in looking at how cognitive impairment changes before a diagnosis, with the eventual hope that if we can understand that pattern, perhaps we can intervene before irreparable damage. And finally, we looked at individuals whose data had no missing SDMT scores or that disease burden score. After doing this filtering, we looked at roughly 3,700 individuals, and the censoring rate was 85%, meaning their diagnosis, 85% of the individuals, we did not know when they were diagnosed. So we applied these 5 different methods, and I'll walk you through the results. 2 of those methods is something called an inverse probability weighting and an augmented version of that. By design, the augmented version is supposed to have higher efficiency, meaning lower variability. In other words, we're supposed to have smaller standard errors here compared to these numbers. But if you look at the results, all of these numbers are higher than the augmented numbers are higher than the regular numbers. Now, unlike when we first started this project, these results were not surprising to us because since we really dug deep into these methods, we had proven that the augmented version will indeed be more efficient than the regular version, but one of the distributions involved has to be correct. If that distribution is wrong, this augmented version will be wrong. And we don't think we modeled this correctly because of, first of all, this weird result with the efficiency, but also because of the following results. So other scientists have shown that cognition declines as you get closer to a diagnosis. So this SDMT score, the higher your score is, the more cognition you have, the lower means you're losing cognition or you have cognitive impairment. So we were expecting to have this negative slope relationship, but our results are showing a positive slope relationship. It's saying that your cognition improves as you get closer to diagnosis, which makes no sense. Another method that we had considered was something called maximum likelihood. And with this one, it's also sensitive. You have to correctly specify a distribution, otherwise the results make no sense. And that's what's happening here. Other scientists have shown that, again, cognition declines for high disease burden scores. So we expect a negative slope. Our results are showing a positive slope, so the complete opposite. Finally, we had these 2 other methods called a complete case and augmented complete case. The augmented version is supposed to have smaller variance, supposed to have smaller standard errors. And if you compare the augmented numbers to the regular numbers, indeed, these numbers are smaller than these ones consistently. Now, the augmented complete case, it also has some sensitivities. You need to correctly model this distribution. But this distribution isn't as hard to model as the other ones because these data, the delta, y, and z, they're always observed. So we have a good chance at modeling those correctly. And we believe we did a good job because of the following results. We expected this negative slope, cognition to decline, and our numbers agree with that. Similarly, We expect cognition to decline as you get higher disease burden scores. We expect a negative slope. We got a negative slope. So if you were to compare these results between complete case and augmented complete case, the results do look very similar, with the main difference being that the augmented versions have smaller standard errors. So based on these results and our very extensive simulation study, we actually prefer this augmented complete case method because it is quite robust and it has quite high efficiency. So in summary, we encountered these challenges. We had to rethink how we approached this problem. We were able to identify 5 different methods and show how they differ between when X is missing and X is right-censored. And it also opened an opportunity in that, is there a method that we can develop that is highly robust? We can be very wrong and still be right, and also efficient. This is a problem that my lab and I are working on right now. So I just want to conclude by sharing a little bit about me in terms of my background. So I was born in Lima, Peru. And when I was a little girl, my parents wanted to come to the US to study. My dad wanted to study his PhD and my mom her master's. So we ended up moving to the US. We started in Iowa and eventually relocated to California. So in terms of my culture, I feel like I grew up in 2 worlds. My home life was very much Peruvian. We ate a lot of yummy Peruvian food. We celebrated Peruvian culture. My kids, their favorite food right now is mac and cheese. When I was a little girl, my favorite food was something called papa la huancaína, which is potatoes with this really yummy sauce. Now, so that was my Peruvian world. My outside world was very American, very Californian. And sometimes those 2 worlds clashed. One particular instance was when I was in high school. In my sophomore year, I had signed up for this honors English class. And my teacher, she came up to me and just said, look, you're never going to be a great writer because you speak 2 languages, and you'll never be able to fully understand what makes good English writing. Now, looking back, that was a very ignorant comment, and it definitely affected me when I was a teenager. Thankfully, though, it didn't shatter my confidence. I ended up building my craft so that these days, my success rate in terms of getting awards and grants is about 80%. Not only that, I've developed my craft to develop this tutorial that I call Create Spicy Science, where I teach other trainees how to write compelling scientific writing. And so far, out of my 35 trainees, they have achieved 71 and counting achievements, including prestigious awards from NSF, NIH, and other foundations that I'm incredibly proud of the work they do. So thank you for your attention. I'm happy to take questions at this time.